Imagine you hold a magical box in your hands, small enough to fit on your desk but powerful enough to shape reality itself. You can ask it for an apple and an apple appears. You can ask for a pencil and it's there. You can even ask for a unicorn and somehow, there it is, standing before you in all its fantastical glory. But here's the twist. The box doesn't decide what to create until you open it. Before you look inside, it could be preparing anything at all, but the moment your eyes meet its contents, it locks into a single reality. Suddenly, it is not a universe of endless possibilities anymore, it is one object, one truth. This strange and magical behavior mirrors the way the quantum world works. Tiny particles, smaller than anything you can see, exist in a superposition, a state where they are many things at once. Only when they are observed, measured, or interacted with do they settle into one definitive state. Physicists call this the collapse of the wave function. The act of observation is not passive, it actively shapes reality, forcing the universe to pick a path out of infinite possibilities. This idea challenges everything we take for granted about cause, effect, and reality itself. For centuries, humans have sought to understand the building blocks of the universe. The ancient Greeks imagined everything made of 4 elements: air, fire, water, and earth. That was revolutionary for its time, an attempt to reduce the boundless diversity of nature to a few fundamental substances. Centuries later, scientists like John Dalton proposed atoms as the true indivisible units of matter. Then came Max Planck, Albert Einstein, Niels Bohr, and countless others, revealing that atoms themselves were composed of even smaller, stranger entities, behaving in ways that defied classical physics. Today we know that the universe is made of subatomic particles, electrons, quarks, neutrinos, and more, all weaving a complex, invisible web of matter and energy. But even this is just scratching the surface. Quantum theory suggests that these particles are excitations of underlying fields that permeate the very fabric of space and time. Particles are not isolated points, they are peaks in an ocean of energy. Waves ripple through the unseen fields, giving rise to the tangible universe we interact with. Understanding this requires letting go of intuitive assumptions about how reality should work. Things can be in 2 places at once, probabilities reign supreme, and certainty is an illusion. This is not fantasy. It is the science that governs every atom in your body, every photon of light around you, every particle that forms stars, planets, and galaxies. To bring this strangeness closer to home, consider a simple atom. It has a dense nucleus surrounded by electrons, invisible dancers whirling in probabilistic patterns. The protons and neutrons at its center are made of quarks, which themselves follow rules that seem absurd from a human perspective. Electrons are not tiny balls orbiting neatly like planets around a sun. They exist in clouds in ranges of probability, collapsing into a specific position only when observed. These tiny structures interact with 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Every chemical reaction, every spark of light, every heartbeat emerges from this delicate interplay. And yet, even at this fundamental level, nature refuses to be pinned down. The Heisenberg uncertainty principle tells us that certain pairs of properties, like an electron's position and momentum, cannot both be known with arbitrary precision. The universe, at its core, is fuzzy, unpredictable, and astonishingly beautiful. Now imagine scaling up this behavior to the scale of everyday objects. This is what Erwin Schrödinger did in his famous thought experiment. He imagined a cat sealed inside a box with a vial of poison triggered by the decay of a radioactive atom. According to quantum theory, until someone looks inside, the atom is both decayed and undecayed, and the cat is simultaneously alive and dead. The paradox brings the microscopic strangeness of quantum mechanics into a macroscopic, almost cinematic reality, highlighting how profoundly counterintuitive nature can be. Yet this is more than a mind trick. It illustrates that reality does not exist independently of observation in the way we often assume. This has puzzled and fascinated physicists for nearly a century. Some interpret it through the Copenhagen interpretation, which focuses on practical calculations rather than metaphysical speculation. Others propose parallel universes where every possible outcome occurs. The debate is ongoing, but the effects of quantum behavior are undeniable. Light can behave as both a particle and a wave. Energy is quantized. Particles are fleeting excitations of invisible fields, constantly popping in and out of existence. Even the void is alive with virtual particles that blink into reality and vanish, a seething, unseen foundation of everything around us. As strange as this may seem, it is consistent, precise, and predictive. Physicists can calculate probabilities to astonishing accuracy, guiding everything from semiconductor technology to quantum computing. But beyond calculation lies wonder. The quantum world teaches us humility, revealing that the universe is far stranger than our senses suggest. We are not merely passive observers. The universe responds to interaction, measurement, and inquiry. Our understanding of reality is shaped as much by our questions as by the answers the cosmos provides. The first chapter of this journey into quantum reality is an invitation to see the universe not as a fixed stage, but as a dynamic, probabilistic theater where particles dance, possibilities flourish, and observation itself becomes a player in the cosmic story. As we move deeper, we will uncover how these invisible actors, the electrons, quarks, neutrinos, and fields, combine into atoms, molecules, stars, and galaxies, building everything we see, while still obeying rules that defy intuition and invite endless curiosity. As we leave the magical box behind and let the ideas of Schrödinger's cat linger in our minds, we start to see that reality is not just stranger than we imagined, it is stranger than we can imagine. Atoms and subatomic particles form the visible world, yet they themselves are manifestations of deeper fields, vibrating and interacting in ways that defy everyday logic. Imagine for a moment an orchestra where every instrument exists in every possible state simultaneously, yet as soon as you look at one, it plays a single, distinct note. The universe, at its most fundamental level, behaves like this cosmic symphony. But unlike music, this symphony is invisible to our senses. We rely on instruments, experiments, and mathematics to perceive its patterns. Consider light. Sometimes it behaves as a wave rippling smoothly through space, and other times it behaves as a particle, striking detectors at discrete points. The very concept of what light is becomes fluid depending on how we interact with it. This wave-particle duality is not a quirk. It is the heartbeat of quantum reality. Scientists have explored these phenomena for over a century. Experiments with double slits, interference patterns, and photons reveal that particles can interfere with themselves, exist in multiple locations at once, and even influence outcomes without direct interaction. Imagine throwing a stone into a pond and finding ripples appearing not only where the stone lands but simultaneously in distant parts of the pond, as if the water knows in advance. That is how the universe behaves at the tiniest scales. And yet, for all its strangeness, quantum mechanics is not chaotic. There is order hidden in the apparent unpredictability. Probabilities govern outcomes, and mathematics describes these probabilities with staggering precision. Each particle carries minimal properties, mass, charge, and spin, but these are enough to fully define its behavior within the universe's rules. With this tiny set of characteristics, particles combine into atoms, which combine into molecules, which in turn form the stars, planets, oceans, and even our own bodies. The cosmos emerges from simplicity wrapped in complexity, elegance hidden beneath apparent randomness. But even as we trace matter from the tiniest quarks to colossal galaxies, the question of observation looms large. Do particles require a human observer to choose a reality, or is any interaction sufficient? Physicists have debated this for decades. Some interpretations suggest consciousness itself plays a role in collapsing the wave function, while others propose that interactions with the environment, the mere act of particles bumping into each other, resolve possibilities into reality. Both ideas challenge our notions of objectivity and reality. Meanwhile, experiments continue to push the boundaries. Quantum entanglement, famously described by Einstein as spooky action at a distance, shows that particles can remain mysteriously connected even when separated by vast distances. A change to one particle seems to instantaneously influence its entangled partner, defying classical concepts of space and time. This entanglement is not just a theoretical curiosity, it has real-world implications. Quantum cryptography, teleportation of information, and the development of quantum computers all rely on these bewildering connections. Imagine sending a message across the universe, knowing that it is secured by the fundamental rules of quantum mechanics, unhackable, instantaneous, and rooted in the very fabric of reality. Yet with all this wonder comes paradox. The many-worlds interpretation, for instance, proposes that every possible outcome of every quantum event actually occurs, but in a separate, branching universe. In one world, a particle decays, in another, it doesn't. In one universe, Schrödinger's cat lives, in another, it dies. These parallel realities, if they exist, suggest that our own experience is just a single thread among infinite possibilities. It stretches the imagination to consider that somewhere, beyond our perception, countless versions of ourselves live out different choices and outcomes. Still, most physicists focus not on speculation but on what can be measured, predicted, and applied. Quantum mechanics, as strange as it is, offers predictive power that has revolutionized technology. Lasers, semiconductors, MRI machines, and even the transistors powering your devices all rely on principles derived from these tiny, elusive entities. The theory works flawlessly, yet its philosophical implications remain a playground for thought. And the deeper we go, the stranger it gets. Quantum fields, the foundation of reality itself, are alive with fluctuations. Even in the emptiest space, virtual particles appear and vanish, shimmering into existence and fading in an eternal dance. These fluctuations may have seeded galaxies in the early universe or influenced the evolution of cosmic structures. The universe is not a static backdrop. It is dynamic, active, and intertwined with its own quantum underpinnings. As we trace these threads, we also encounter the limits of intuition. Cause and effect are not as straightforward as they seem. At quantum scales, uncertainty is intrinsic. Even with complete knowledge of a system, predictions can only be probabilistic. The universe resists being pinned down, reminding us that our assumptions, biases, and mental models are just tools. They are not reality itself. We begin to see that understanding the cosmos is not simply about accumulating facts. It is about cultivating a sense of wonder, embracing the counterintuitive, and following where the universe leads. Each experiment, each observation, and each calculation is a dialogue between human curiosity and the laws of nature. And this dialogue is ongoing. Quantum physics is not merely an abstract pursuit. It is a lens through which we can reimagine existence. It challenges our notions of time, space, identity, and causality. The universe is stranger than it seems, yet this strangeness is ordered, coherent, and breathtaking. Chapter 2 leaves us standing at the threshold of deeper mysteries. We have journeyed from atoms and quarks to quantum fields and entanglement, glimpsing how observation shapes reality and how particles defy classical expectations. Ahead, we will explore how these principles influence matter, energy, and even life itself, diving further into the cosmic story of the invisible forces that structure everything we see and touch. The quantum universe is vast, intricate, and alive, and each revelation brings with it both answers and deeper questions. As we journey deeper into the quantum landscape, the universe begins to reveal layers of complexity that defy everyday perception. What once seemed like empty space is now alive with activity. Invisible fields stretch across the cosmos, undulating with energy, giving rise to particles that blink into and out of existence. The universe is less like a static stage and more like a living tapestry, woven from waves, probabilities, and fleeting interactions. Imagine standing at the edge of a dark ocean, watching the surface shimmer with unseen currents and sparks of light that dance unpredictably. Each spark represents a particle, a possibility, a manifestation of the underlying quantum field. And yet, these flickering events are not chaotic. They follow precise mathematical rules, forming the foundation upon which reality builds itself. The world we perceive, tables, trees, mountains, and oceans, is a collective expression of countless quantum events layered together over time. Electrons orbiting nuclei, quarks inside protons and neutrons, and even the forces binding them are all tiny actors in a drama that spans the cosmos. Each particle carries its properties, mass, charge, spin, but these few numbers are enough to define an entire universe of interactions. Even more astonishing is that particles can exist in superpositions, embodying multiple possibilities simultaneously. Their potential is vast until observed, when a singular outcome is revealed. This principle lies at the heart of quantum computing, where qubits can encode multiple states at once, offering a computational power unimaginable with classical systems. But the quantum world is not only about probabilities, it is also about connections. Entangled particles can affect each other instantly across vast distances, challenging our traditional ideas of space and causality. Imagine two dice rolling in perfect harmony, separated by galaxies, each reflecting the outcome of the other without any apparent communication. These correlations have been confirmed in countless experiments, proving that the universe is deeply interconnected in ways we are only beginning to understand. Yet for all its strangeness, the quantum universe is not inaccessible. Scientists have devised ingenious ways to measure and manipulate these phenomena. Particle accelerators smash atoms together at near-light speeds, revealing fleeting particles that exist for fractions of a second but illuminate fundamental truths. Lasers trap individual atoms, allowing researchers to observe their behavior in isolation. Quantum sensors detect minute changes in magnetic and gravitational fields, hinting at unseen forces and subtle interactions. And through these experiments we gain not just knowledge but perspective. We begin to understand that reality is not a fixed backdrop but an intricate interplay between matter, energy, and observation. Every measurement, every interaction, is a conversation between the observer and the observed, shaping outcomes and revealing patterns. The universe, it seems, is participatory. As we explore further, questions arise that are as philosophical as they are scientific. Does consciousness play a role in determining reality? Or is the universe indifferent, with outcomes collapsing simply through interaction with other systems? Interpretations abound, from the Copenhagen view, which emphasizes practical calculations and collapses upon observation, to the many worlds idea, where all possibilities occur in branching, parallel universes. No experiment to date has decisively favored one over the other. The lack of definitive answers does not diminish the power of quantum mechanics. Rather, it highlights the richness and mystery of the cosmos. Even the void itself, seemingly empty, is filled with virtual particles flickering into existence. These ephemeral entities may carry energy, influence cosmic expansion, or shape the earliest moments of the universe. The very notion that nothing is active, vibrant, and energetic challenges our intuition and expands our sense of what reality can be. And yet, despite these paradoxes, the universe obeys rules that are consistent, precise, and predictive. Physicists can calculate probabilities for particle interactions to astonishing accuracy, guiding technologies from transistors to quantum cryptography. These applications, tangible in our everyday lives, are a testament to humanity's ability to navigate and harness the bizarre laws of the subatomic realm. As we peer into the foundations of matter, we also glimpse the edge of life itself. Quantum processes underpin chemical reactions, photosynthesis, and even aspects of neural activity. Some theorists speculate that quantum coherence in biological systems might influence consciousness, although this remains controversial. Regardless, it is clear that life, in all its complexity, emerges from quantum rules. The very processes that make stars shine and planets form also give rise to the delicate machinery of cells and molecules. And through it all, observation remains central. Reality is not separate from the act of seeing, it is intertwined with interaction, measurement, and engagement. By asking questions and performing experiments, we shape our understanding and, in subtle ways, the reality we observe. The cosmic dance of particles, waves, and fields is not merely a scientific curiosity, it is a mirror reflecting our quest for knowledge, our desire to understand the universe and our place within it. As Chapter 3 draws to a close, we stand on the threshold of even deeper mysteries. We have explored the hidden activity of quantum fields, the strange duality of particles and waves, the invisible threads connecting entangled entities, and the astonishing ways these principles influence matter, energy, and life. Ahead lies a journey into the far reaches of quantum mechanics. The interplay between fundamental forces, the emergence of classical reality from quantum possibilities, and the philosophical implications that challenge our very notions of existence. The universe continues to beckon, strange and beautiful, a cosmic story written in waves, probabilities, and light. As we step into the final chapter of our quantum journey, the universe begins to feel both intimate and infinite at the same time. Every particle, wave, and field we have explored is a note in the grand symphony of reality, each vibrating with unseen energy and participating in an intricate cosmic dance. What once seemed separate, the observer and the observed, the particle and the wave, matter and energy, reveals itself as deeply connected, intertwined, and inseparable. Imagine standing at the edge of a boundless city made of lights, where each flicker represents a particle, a decision, a probability collapsing into reality. You can see the patterns emerging, the rhythms of creation, yet the full scope remains just beyond perception. In this city, every interaction matters. A particle here nudges another there, an observation changes the outcome, and a ripple can travel across space and time, influencing events in subtle ways. It is a universe where probabilities are as real as concrete objects, where certainty is a privilege reserved only for classical illusions. In this quantum reality, even the simplest things, an apple on a table, a beam of light, a human thought, are built from the same mysterious, vibrating threads. The fundamental forces, gravity, electromagnetism, and the strong and weak nuclear interactions, intertwine with quantum fields to orchestrate the cosmos. Stars ignite, planets form, life emerges, and consciousness arises, all governed by these subtle, precise, yet profoundly strange laws. And yet, for all its complexity, the universe is understandable. Through careful observation, rigorous experimentation, and mathematics, we can predict behavior, harness forces, and even manipulate quantum phenomena to build technologies that were once the stuff of dreams. Quantum computers, unbreakable encryption, lasers, and particle detectors are the tangible fruits of engaging with reality on this deep level. But the story does not end with practical applications. Quantum mechanics invites philosophical reflection, challenging assumptions about reality, causality, and identity. The notion that observation shapes outcomes, that multiple possibilities can coexist, and that entanglement links distant entities forces us to reconsider what it means to exist, to act, and to perceive. Some interpretations stretch the imagination further still. The many-worlds perspective suggests that every possible outcome of every quantum event occurs, creating an infinite branching of universes. Somewhere, countless versions of you live out choices that never materialized here. Somewhere, cats live and die simultaneously in ways we cannot fathom. This is not merely science fiction. It is a consequence of taking quantum theory seriously, a theory verified again and again through experiment. In contemplating this, we recognize our own place within the quantum tapestry. Our actions, measurements, and inquiries are threads that weave into the broader fabric of reality. Curiosity itself becomes an act of participation, a way of engaging with the deepest structures of the cosmos. And yet, even as we probe ever deeper, mystery remains. Why does the universe obey these rules? Why do particles behave probabilistically? Why is there more matter than antimatter? These questions may never have definitive answers, yet they fuel the pursuit of knowledge and imagination. This final chapter is not just about understanding quantum mechanics, it is about embracing the profound strangeness of reality. It is about marveling at a universe where emptiness teems with energy, where observation creates reality, and where the simple act of asking a question shapes the answers we can receive. As we reflect on the journey from atoms to quarks, from quantum fields to entanglement, we begin to see a universe that is beautiful, elegant, and awe-inspiring in its complexity. Each particle, each wave, and each interaction is part of a story that spans from the beginning of time to this very moment, including us. Reality, when seen through the lens of quantum mechanics, is a story of connection, possibility, and wonder. It challenges intuition but rewards imagination, precision, and curiosity. And perhaps the most astonishing lesson of all is that we are participants in this story, observers who can glimpse the hidden symphony, ask questions, and expand our understanding. The universe is alive with mystery, yet accessible through thought, observation, and exploration. Our journey through the quantum world concludes not with answers to every question but with a profound appreciation of the elegance, strangeness, and beauty of existence itself. Reality is not simply what we see, it is the dance of possibilities, the interplay of forces, and the collapse of infinite potential into tangible experience. And within this dance we find both knowledge and wonder, understanding and mystery, a cosmos that is at once comprehensible and infinitely enchanting.